So today we're going to talk about exponents and logarithms and then exponential and logarithm functions. It's pretty conceptually intuitive material, I think, but there are a lot of relatively challenging problems to go over. So with that said, let's get started. So what are exponents? Let's start with something very, very basic. Exponentials are just a shortcut for writing multiplication of a number by itself many, many times. So in the same way that we defined multiplication as a way of repeating addition, 2 plus 2 plus 2 plus 2 is 2 times 4. You're going to do something similar here with exponents. If I have a times itself n times, I'm going to call that a to the power of n. And notice here that I'm putting a 1 times in front of this product. And it's because when you're multiplying, you have to start with something. You can't multiply out of nowhere. And that's going to be relevant because it means that if I do a to the power of 1, I get a. And if I do a to the power of 0, I get 1 because I start with 1 and I haven't multiplied yet by a. So as a quick example, if I had 2 to the power of 7, that's 2, 4, 8, 16, 32, 64, 128. So exponents with 0, like I said a second ago, if I'm raising a number to the power 0, then because I have to start my multiplication somewhere, and I haven't multiplied by a any times yet, I actually start at 1. If I was starting at 0 and I multiplied by a, I would never be able to get away from 0. And we say that 1 is the multiplicative identity, which means it's the only number that I can multiply by something without changing that something. All right, and this also works somewhat confusingly if you have 0 to the power of 0. So 0 to the power of 0 is also 1 because I haven't yet multiplied by 0 if I'm doing 0 to the power of 0. I multiplied by 0 no times, and I'm starting with 1. Then rules for multiplying exponents, for combining exponents. If I have two exponents that are in the same base, so I have a to the n and a to the m, and I multiply them together, if you write it out, you'll notice that I have a product of n a's and a product of m a's, which means in total that I have a product of n plus m a's, which means I can write it as a to the power of m plus n. And that's a rule that you have in general. So for example, if I have 5 to the third times 5 to the fourth, that's going to be 5 to the power of 3 plus 4. In other words, 5 to the 7. Negative exponents. Exponents can be negative. If you consider a to the n times a to the negative n, then using the rule that we just derived, I can write that as a to the n plus minus n, so a to the n minus n, which is a to the 0, and we know that that's 1. And that means that if I isolate a to the negative n by dividing both sides by an, then I'll find a to the negative n is 1 over a to the n. And that's another rule that you have in general. So for example, 2 to the minus 5 is just 1 divided by 2 to the 5, which is 1 over 32. By the way, we're going to move through all of the rules for exponents, then we'll do a couple of exercises and go from there. Okay, now the exponent of a product and quotient. So if I have AB to the power of n, then if I wrote that out, I would have AB, AB, AB in my product, and I can rearrange the terms because multiplication doesn't depend on order, and I'll find a to the n and b to the n, a to the n times b to the n. Something similar for quotients, you just kind of use the rule above with the rule from the previous slide, which was uh, if I have 1 over b, I can write that as b to the negative 1. So I can write this as ab to the negative 1 all to the n. And if you simplify all of that, you'll find that this is equal to a to the n times b to the negative n, or a to the n over b to the n, whichever is more intuitive for you. So quick example, if I have 6 to the power of 5, I can write 6 as 3 times 2, and that's all to the power of 5. So that becomes 3 to the power of 5 times 2 to the power of 5. If I have 3 halves to the power of 4, then I can write that as 3 to the 4 over 2 to the 4. That's 81 over 16. Given that I know that a to the n times a to the m is equal to a to the n plus m, and that a to the negative n is 1 over a to the n, then if I have a to the n divided by a to the m, I can write that as a to the n times a to the negative m, which is going to be a to the n minus m. So for example, if I have 3 to the 6 over 3 to the 3, I'm just going to get 3 to the power of 6 minus 3, and that's going to give me 3 to the 3, which would be 27. If I have an exponential of an exponential, so I have a to the power of m all to the power of n, I want you to think about writing out a to the m as a times a times a times a m times. That's what's going on in this term here. And then I'm going to write that times itself a total of n times. So each term with m a's is going to be repeated n times. So how many a's am I going to have in total? I'm just going to have m times n a's. So a to the m to the n is going to be a to the m n. Let's do an example. If I have 27 to the 4, I can rewrite 27 as 3 to the 3 all to the 4. And that's going to give me 3 to the power of 12. 3 times 4. All right. Now, I'm going to give you a minute to try a simple exercise. So, I had 2 to the 2 to the 3 over 2 times 2 to the minus 7 times 2 to the 3, and the 8 is actually the power 1 over 3. That's all raised to the power 2 over 16 to the minus 1. Okay, I can rewrite that as, I'm going to distribute the 2's into the exponent, so 2 to the 2 to the 3 times 2 to the minus 14 times 2, and then 2 to the 3 to the 1/3. This is just going to be 2, and then I'm going to put that to the power 2. And that's all over 2 to the power of minus 4, because 16 is 2 to the 4, and it's being raised to the minus 1. Okay, that means that I have 2 to the 6 minus 14 plus 2 over 2 to the minus 4. The numerator is going to give me 6 minus 14 is minus 8, plus 2 is minus 6, and I do 2 to the negative 6 divided by 2 to the negative 4 will give me 2 to the negative 2, which is 1 over 2 squared, and that is 1 over 4. Okay, perfect. Okay, I want to talk quickly about the connection between exponents and roots, right? So we have seen the square root before, we've seen the nth root probably before, but the nth root of a is a number that when raised to the power of n gives me a. So if I have nth root of a to the power of n, I get back a. And when n is an even number, then a must be, the inside of the square root must be greater than or equal to 0 if n is even. And then the root returns positive values even though negative b squared is equal to b squared. So if you have a square root of 16, that's 4, even though negative 4 squared also gives 16. So you should remember the square root always outputs a positive number, which is why if you square root both sides, you need to add a plus or minus. And if I write a as a to the power of 1, I notice that the nth root of a to the power n is the same thing as a to the 1, which means that I must have that the nth root of a on its own is equal to a to the power of 1 over n. Because remember, raising a power, an exponent to a power is the same as multiplying the powers. So whatever power represents the nth root of a, when I multiply that by n, I should get 1. So it must have been 1 over n. And then if I raise both sides to the mth power, you find the general result, which is a to the power of m over n is the nth root of a to the m, okay? Which is the same thing as the nth root of a all to the m. So a quick example, if I have 27 to the power of 4 over 3, that's the same thing as the cube root of 27 to the power of 4, and the cube root of 27 is 3, and that to the power of 4 is 81. Okay. So here's another example. I'm going to give you a minute to do this one too. Okay, let's go over this. I want to start by taking that root 12 in the numerator, and I'm going to write that as 2 root 3, because 12 is 4 times 3, and the square root of 4 is 3, which means in the numerator I actually have 2 root 3 times 2 root 3, and then in the denominator I have the cube root of 27, and that's 3. Okay, and I'm doing all of that to the power of 3. So if I rewrite the inside before I expand everything that I have here, I'm going to have 2 root 3 times 2 root 3 is just going to be 12 because 2 times 2 is 4 and root 3 times root 3 is 3 over 3 to the 3. 12 over 3 is 4 and 4 to the power of 3 is 64. Next. Okay, so now that we've kind of understood the basic rules that we have for exponents, I want to talk about exponential equations. So if you have a left-hand side and a right-hand side that are equal and they have the same base, so I have a to the power of n is equal to a to the power of m, then n and m have to be the same. I can't have two different powers. Now, exponentials can also appear in equations with one or more unknown. So for example, I could have the equation 1 over 2 all to the power of x minus 1 is equal to 8 to the power of x plus 1. And what I would do here is rewrite 1 over 2 as 2 to the minus 1, and putting that to the power of x minus 1, I can equate to the other side 2 to the power of 3 to the power of x plus 1. And then I just use my exponent rules to turn this into 2 to the 1 minus x is equal to 2 to the power of x, 3x plus 3. Now, I can equate the exponents, like I said. 1 minus x is equal to 3x plus 3. And that's going to imply, if you solve the equation, that x is equal to minus 1 over 2. Now, it's worth mentioning, I said that if two exponents of the same base were equal, that the exponents were equal. That's true if the base is not 0, right? Because if I can have 0 to the power of 5 is 0, and 0 to the power of 10 is 0, they're always going to be the same. But for non-zeros and also not for 1, it's going to be true. Okay, let's go over the solution here. So the first thing I want to do is recognize that 2 to the power of 0 is 1, right? Because anything raised to the power of 0 is going to give me 1. And if I bring that to the right-hand side, I can write 2 to the 4x plus 1 is equal to 32. And I recognize that 32 is 2 to the power of 5, which means that 4x plus 1 is equal to 5, and solving that gives x is equal to 1. Nice. Let's continue. Now, another important skill related to these exponents and surds is rationalizing the denominator. So if I have a fraction that has an irrational denominator, which is something of the form 2 over 3 minus root 2, for example, we can rationalize the denominator by multiplying the top and bottom by the opposite irrational number, in this case 3 plus 2 root 3. And when I say irrational number, I mean that the square root of 2 cannot be written as a fraction. And we'll talk about that more for the higher level students when we do proof and reasoning. But for the moment, just know that the square root of any number that isn't a perfect square cannot be written as a decimal, or sorry, as a fraction, right? So I rationalize the denominator by multiplying by the opposite irrational number, and if I expand everything out, I'm going to get 2 times 3 plus root 2 is going to give me 6 plus 2 root 2, and then in the denominator, 3 times 3 is 9. Then 3 times root 2 is 3 root 2, minus root 2 times 3 is negative 3 root 2, and then minus root 2 times root 2 is going to be minus 2. The key here is to notice that the terms with root 2, or the terms with the root in general, are going to cancel each other out because I've multiplied by the opposite term. So it's basically going to give me a difference of squares, and I can ignore the square roots. So I'm going to get 3 squared minus root 2 squared is 9 minus 2 is 7. Okay, so I have in the denominator, I have 2 minus 3 root 2. So I'm going to multiply by the opposite complex, not complex, the opposite irrational number, which is 2 plus root 2. So I'm going to do 2 times 2 plus 3 root 2 over 2 minus 3 root 2, 2 plus 3 root 2. But 4 plus 6 root 2 over, and it's not. Then I'm going to have 2 times 2, and I'm going to do minus 3 squared times root 2 squared. Okay, so that's going to be 2 squared minus 9 times 2, that's 18. So this becomes 4 plus 6 root 2 over negative 18. Sorry, negative 14, because I have the 2 squared. All right, and if I want to simplify that, I'll factor out 2 from the numerator and denominator, and I'll put the negative in front. So negative 2 plus 3 root 2 over 7. Okay, so that's option number 3. We're going to talk about logs now. And logs are a mathematical tool that allow us to ask the question, what power of a given base gives a specific value? And that might sound like a bit of a word soup, so let me give you an example. If I know that a to the power of x is equal to b, then I can write that log base a of b is equal to x. Now, what am I saying when I do that? Basically, when I use a log, I'm trying to find the exponent that would have made something true. I'm trying to find what exponent I can put on a to get b in this case. So I do a to the power of x gives me b, and so log base a of b is x, okay? And the base must be positive, because otherwise it wouldn't work for, you can't raise a negative number to anything other than an integer, because that would be doing the equivalent of a square root. So the value of x, however, can be any real number. So let's do a specific example. If I have log base 5 of 125, that means what power of 5 makes 125? And we know that 5 cubed is 125. So the log base 5 of 125 is 3. I don't know why I wrote 5. That should be 3. Now, log base 3 of 1 over 9 means what power of 3 makes 1 over 9? And since 1 over 9 is equal to 1 over 3 squared, and that's 3 to the minus 2, I can say that log base 3 of 1 over 9 is minus 2. So at the standard level, the log that you're most often going to see is log base 10. So log base 10 is very, very useful because we use a base 10 system. We have 10 fingers and we count things in base 10, 10, 100,000. And so the log base 10 gives us a sense of the order of magnitude of something, how many powers of 10 go into it. So for example, if I have log of 0.001, then 0.001 is 1 over 1,000, or 10 to the minus 3. So log of that is minus 3. And I didn't explicitly mention this, but log base 10 is used so commonly in science and math that we actually just use the shortcut log to denote log base 10. So if you see a log and it doesn't tell you the base, it's because it's a log in base 10. So 1,000 is 10 to the power of 3, and log is just log base 10. So I'm doing what power of 10 gives me 10 to the power of 3? The answer is 3. Now the natural log. This is another special logarithm, and it's the one in base e, which is Euler's number. And we haven't talked about it yet. It's going to show up a lot in the course. It's one of those numbers, a little bit like pi, that is so special in math that it deserves its own letter. And it is going to have all sorts of interesting properties that are going to be useful, especially in calculus. But for the moment, I'm just going to tell you that e is approximately 2.7. And we're basically asking what power of 2.7 is going to give me the log that I'm looking for. So log base e is the same thing as ln. So if I do ln of e to the power of 3, what power of e gives me e to the 3? Just 3. So I want you to evaluate this log. I have ln of the cube root of e to the 4. I'm going to give you 10 seconds. Okay, so let's remember what I know about surds. I know that the cube root of e to the 4 is the same thing as e to the 4 over 3. And then the log is asking me what power of e gives me e to the 4 over 3. Well, it's just going to be 4 over 3. So some tricks for evaluating logs. If you have a log, since a log base a of b being equal to x means that a to the x is equal to b, then if I know the powers of some shared base, I can usually evaluate a log without using a calculator. So if I have log base 81 of 27 is equal to x, that means that 81 to the x is equal to 27, right? That's what we know from the definition of the log. But I know that 81 is 3 to the power of 4, and I know that 27 is 3 to the power of 3. So if I have 3 to the power of 4x, right, 81 is 3 to the power of 4, to the power x is 3 to the power of 4x, and that's supposed to be equal to 3 to the power of 3. which means that 4x is equal to 3, which means that x is equal to 3 over 4. All right. Now, at the standard level, you're not really going to be expected to do that. If you're being asked to evaluate a log that isn't either log base 10 of some even power of 10 or ln of some even power of e, then you're actually just going to use your calculator. Your calculator can do log in base 10, it can do ln, and it can do logs with any specific base that you want. So if you try and do log base 3 of 5 on your calculator, you'll get 1.46. So I'm going to give you a minute to evaluate each of these on your calculator. So I'm going to show you on a TI-84. It's going to be very similar no matter what calculator you're using. And in part A, we're looking for log of 19. Remember, log is log base 10, but your calculator will actually just have a log key. So I do log of 19, and I find 1.27, which rounds to 1.28. Okay, so that's the answer for part A. Part B is asking us for ln of 4, and ln, if I remember, is right here. So ln of 4, that's going to give me 1.38, which if I round that up to 3 significant figures, that's 1.39 is the answer. And then part C, we're asked for log base 7 of 6. So this one you're not going to find immediately on the keyboard. What you can do is if you hit math and you scroll down, you will find log base. And then you'll get something like this, and you can just type in, I want log base 7 of 6. And that's going to give me 0.921. Remember, if rounded to 3 significant figures. So let's go back to the answers. And I had 1.28, 1.39, and 0.921. So let's start talking about the laws and rules of logs. So if I have a sum of logs, if I have log base a of x plus log base a of y, I want you to remember that the log is asking the question, what power of a is going to give me x now? I know that a to the power of log base a of x is equal to x, and similarly that a to the power of log base a of y is equal to y. All right, so I'm going to multiply these two things together and see what happens. I'm going to multiply them, and I get a to the power, and remember, if I have a product of exponents in the same base, I can add up the exponents. So I get log a of x plus log base a of y, and that's going to be equal to x, y, which means that a to the power of log ax plus log ay is equal to xy. Now what I'm going to do is I'm going to take the log and base a of both sides. I'm going to say, what power of a gives me this? So what power of a gives me a to the power of something? Just the power. So log base a of x plus log base a of y gives me log base a of xy. So that is a sort of quick proof of the most common rule that we're going to use in logs, which is the sum rule for logs. If I have log base a of x plus log base a of y, that's the same as log base a of x times y, and vice versa. You can also go the other way. Now, I think you can see how I might show a similar rule for log base a of x minus log base a of y, and that's simply going to give me log base a of x over y. So in this example that we have on the screen, I have ln of 5 minus ln of 3, and I recognize that as a difference of logs both in base e, so I can write that as ln 5 over 3. All right. Similarly, if I have the log base 4 of 2 plus log base 2 of 8, and that's supposed to be log base 4 of 8, that's just going to be log base 4 of 16, which is 2. Now, next rule, the log power rule. So if I know that log base a of x is, let's say log base a of x is equal to y, which means a to the power y is equal to x, then if I raise both sides to the m here, I get a to the y m is equal to x to the m. Okay? And now if I take on both sides, if I take log base a, I get ym is equal to log base a of x to the m. And I remember that y is just log base a of x. So log base a of x to the m is m log base a of x. And that's the so-called log power rule, which says that if I have a power inside the log, I can take that power outside the log as a multiple. So for example, if I have 4 log base 9 of 3, that's the same as log base 9 of 3 to the 4, and 3 to the 4 is 81. Another typo, this is 2. Log base 9 of 81 is 2. Log of this fraction as a sum/difference of logs. Okay, I'm going to give you a minute. I think that's enough time. So let's start with the inside of the log. I have 9 over 27. I can simplify that. So I'm going to have log of a cubed b over 3ab squared. And I can simplify some of the a's and b's. I'm going to get log of, and that's going to give me a squared over 3b, which is going to be using now my rule for the fraction, for a fraction inside a log. This is log a squared minus log 3b. Okay, and log a squared I know is 2 log a, and log of 3b is log of 3 plus log of b, but they're both minus, so log of b minus log of 3. So where is that answer? I think it's number 1. Yeah. All right, so log change of base. This is a slightly trickier rule. I'm not going to really dive into the proof of this one because it's a bit more of a mess. But just know that I can change the base of a log. If I have a log in base a of x, I can write that as log base b of x over log base b of a. And this is in your formula booklet because I know it can be a little bit weird to remember. But if you do want to try and remember, and I think you should, I would just remember that the base of my original log goes in the denominator as the argument of the new log, and then the argument of my original log goes in the numerator as the argument of the old log. Okay? So let's take a look at an example. If I have log base 5 of e, let's try and evaluate that. So I can write that as log base e of e in the numerator divided by log base e of 5. And log base e of 5 is just ln of 5. And I have ln of e in the numerator, that's 1. So I have 1 over ln 5 is my answer. So I'm going to give you 30 seconds for this. Okay, so I'm going to show you 2 ways to do this. I think one of them is harder than the other, but it's also a little bit more systematic. So I'm going to change log base 25 into log base 5. So I can write log base 25 of 125 is equal to log base 5 of 125 divided by log base 5 of 25. And then I recognize that log base 5 of 125 is 3, and log base 5 of 25 is 2, and 3 over 2 is my answer. The way I prefer to think about this question is to know that I'm looking for, if x is the answer, that according to the definition of log, 25 to the x is equal to 125. So 5 to the 2x is equal to 5 to the 3. That also gives me x is equal to 3 over 2. So equivalent methods, but it's up to you which you prefer. 3 over 2. Now I want you to write this as a single logarithm. I'll give you 30 seconds again. Okay, so I have a log base 8 of 6 divided by a log base 8 of 3. And according to my log change of base, that is log base, and I take 3, because that's the argument that's in the denominator. Log base 3 of 6 is the answer. That is number 3. All right, this is still an exercise, but it's a much harder exercise. If you're a standard level student, you can try it. I don't think you really need to be able to do this, but higher level students get cracking. This is a good one. I'm going to give you a minute as well. I'm going to rewrite log base 6 of 12 using a log change of base, and I'm going to change it into base 2 because my p is in terms of base 2. So log base 2 of 12 over log base 2 of 6. That's what I start with. And then I recognize that log base 2 of 12. 12 is 4 times 3, so it's log of 4, log base 2 of 4 times 3, which is log base 2 of 4 plus log base 2 of 3, and that's just p. Now, log base 2 of 4 is equal to 2, so this is p plus 2. And then I can do something similar for log base 2 of 6. That's 2 times 3, so it's going to be log base 2 of 2 plus p is 1 plus p. So the answer is 2 plus p over 1 plus p. That's answer number 3. So this is a quick one, but we can use logs to solve exponential equations. Earlier we solved exponential equations when we had the same base. In general, if I have something like 3 to the x is equal to 7, then if I take the log base 3 of both sides, I find x is equal to log base 3 of 7. That's pretty simple. But let's do an example. I'm going to give you 30 seconds. So I have 4 to the x plus 2 is equal to 20. So I have a base 4 exponent on the left. I'm going to take the log base 4 of both sides. So if I take the log base 4 of 4 to the x plus 2, I'm going to get x plus 2 is equal to log base 4 of 20. And the log base 4, so now if I move x to the right, the 2 to the right-hand side, I get x is equal to log base 4 of 20 minus 2. And 2 is the same thing as log base 4 of 16, because 4 to the 2 is equal to 16. So log base 4 of 20 minus log base 4 of 16. And now I use my difference to quotient rule. So log base 4 of 20 over 16. And 20 over 16 is 5 over 4. Okay, so log base 4 of 5 over 4. Now, finally, we're ready for some exam-style problems. So I'm going to give you a minute to kind of get a head start. If you want to try this on your own, you can also decide to mute me if you don't want to hear my solution, you want to try it on your own. And I'll start in about a minute. I have the log of x minus the log of 3 is equal to 1 plus log of 100. So I'm dealing with logs in base 10, and I'm going to try and simplify the whole left-hand side together and the whole right-hand side together. So I'll start with log x and log minus log 3 is log of x over 3. And I'm going to rewrite 1 as log of 10, log base 10 of 10. That's plus log of 100. And that means that log of x over 3 is equal to log of 1,000. And now what I can do is I can raise both sides. I can exponentiate both sides in base 10, which means the insides of the logs have to be equal. If I have, the same power of 10 gives me x over 3, and the same power of 10 gives me 1,000, then x over 3 has to be equal to 1,000. And that means that x is equal to 3,000. Okay? 3,000. Solve for x in the equation 15 to the negative 3x equals 27 to the 4 minus x. I'm going to give you a minute to get started on this, and then I will solve it. Okay, let me start solving this. So I have on one side 15 to the negative 3x is equal to 27 to the power of 4 minus x. And what I'm going to do, there's different ways to approach these questions when you have an exponential equation. I always think it's easiest to start by taking the log on both sides, and that's going to make it immediately clear what things we can simplify and not. So I'm going to write ln of 15 to the power negative 3x is equal to ln of 27 to the 4 minus x. Okay, now I can use the rule which says that the log of a power is the power times the log of that base. So it's negative 3x ln 15 is equal to 4 minus x ln 27. All right. And now I want to express each of these logs in terms of their prime factors. So 15 is 3 times 5, so negative 3x. And then I can write this as ln 3 plus ln 5 is equal to 4 minus x. And 27 is 3 to the power of 3, so times 3 times ln of 20, sorry, not 27 anymore, just ln of 3. Okay, and I'm just going to make some room. So now if I continue, what do I have? I'm going to try and expand the right-hand side. So I'm going to get negative 3x ln 3 plus ln 5 is equal to 4 times 3 is 12 ln 3, and then minus 3x ln 3. And on the left-hand side, if I expand, I get negative 3x ln 3 minus 3x ln 5. Okay, it's equal to the same thing here. And notice that I have a negative 3x ln 3 on both sides, so I can cancel that. And what am I left with? I'm left with negative 3x ln 5 is equal to 12 ln of 3. Now, if I want to isolate x, I'm going to simply divide by ln 5 on both sides. Negative 3x is equal to 12 ln 3 over ln of 5. Now, dividing by negative 3 on both sides, I get x is equal to negative 4 ln of 3 over ln of 5. Okay, perfect. And by the way, as a side note, I could rewrite this if the question asked me to, using log change of base. And that would be, if I rewrite this as ln of 3 to the minus 4 over ln of 5, this becomes log base 5 of 3 to the minus 4. Of 3 to the minus 4. Okay, but that doesn't matter. We have our answer. Let's just check it. We said negative 4 ln 3 over ln 5. There we go. Something slightly harder now. We have a system of equations with a log in it. So I have ln of x y squared is equal to 7, and ln of y over x is equal to 13. Let's think, before we specifically answer this question, how we normally solve systems of equations. If we have something where we don't have logs, we just have some combinations of x and y equal to something, we have two of them, we can use one of two methods. We can make a substitution, so try and isolate x or y from one equation and plug it into the second, or we can make a combination of the equations either by adding them or subtracting them, or maybe 3 times the first minus the second. And hopefully one of the variables is going to cancel, leaving us with just a normal linear equation that we can solve for one variable. Now that's exactly what we're going to do with these logs. If we choose the right combination of the equations, some of the variables are actually going to cancel, using the fact that the sum of the logs is the log of the products. Okay, so I have inside one log xy squared, and inside the other y over x. And I notice that if I multiply those two together, I have xy squared times y over x. Let me write that out. Xy squared times y over x would just give me y cubed. So I would like for those log arguments to be multiplied together, which means I need to add the logs together. Okay, so ln x y squared plus ln of y over x is equal to 7 plus 13, which is 20. All right, now I can write ln of x y squared times y over x is equal to 20, and my x's are going to cancel. So ln of y cubed is equal to 20, and ln of y cubed is 3 ln y, which makes ln of y equal to 20 over 3. Now let's take a moment to find what x is going to be based on that. So if ln of y is 20 over 3, then I know that ln of y, let me write that better, of y over x is equal to ln of y minus ln of x, and that's supposed to be equal to 13 according to equation number 2. And if I know that ln of y is 20 over 3, and 13 is 39 over 3, then ln of x must be equal to negative 19 over 3. Okay? So if I actually write the answers x and y, I do that by putting e to the power of both sides. So y is equal to e to the 20 over 3, and x is equal to e to the negative 19 over 3. And those are going to be my answers. So in this question, I'm going to have to use my log change of base laws. And I'm going to do that because I want to convert everything to base 2, because I have a log base 4 in the first equation and a log base 2. So I'd like to convert that in the first equation, everything into log base 2. So let me do that. I'm going to say log base 4 of x is log base 2 of x over log base 2 of 4, which is just half log base 2 of x, because log base 2 of 4 is 2. So that means the first equation becomes 3 plus 4 times half is 2, log base 2 of x, is equal to log base 2 of 3y. So I need to do something with this 3, and I can realize that the 3 I can write as log base 2 of 8. So log base 2 of 8 plus 2 log base 2 of x is equal to log base 2 of 3y. So this becomes, I'm going to put the 2 inside there and write log base 2 of x squared. And then I'm going to write, since I have log base 2 of 8 times log base plus log base 2 of x squared, it's going to be log base 2 of 8x squared. And that's supposed to be equal to log base 2 of 3y. And that's going to be my first equation. Or maybe the next step will be easier. I just write 8x squared is equal to 3y. Now, for the second equation, I want to convert that log base 9 of y squared into log base 3. So log base 9 of y squared is log base 3 of y squared over log base 3 of 9, which is half log base 3 of y squared. But I can take out the exponent from the y squared and put it in front, and that would cancel with the 1/2, and this just gives me log base 3 of y. Okay? Perfect. So now I have 1 plus log base 9 of y squared is my second equation on the right-hand side, and I simplified log base 9 of y squared to log base 3 of y. I can write 1 as log base 3 of 3, so that everything on the right-hand side is going to be in log base 3. And then I would have log base 3 of 25 minus 3x is equal to log base 3 of 3 plus log base 3 of y, which means that log base 3 of 25 minus x is equal to log base 3 of 3y. Now I have two logs in the same base are equal to each other. I can equate the arguments. 25 minus x is equal to 3y. And now I have two equations for 3y. I have 25 minus x is equal to 3y, and 8x squared is equal to 3y. So I can equate those two, and that's going to give me the quadratic 8x squared. And sorry, I don't know why I wrote, this is not 25 minus 3x, it's 25x minus 3. I need to correct those. So that's going to be 8x squared minus 25x plus 3 is equal to 0 if I combine the two equations that I have. Now, this is a calculator question, which means I'm allowed to use a calculator to solve this quadratic. If you do, you'll realize that it's 8x minus 1, x minus 3. You can probably also factor this by inspection, but you would have a calculator for this question. And that gives me two solutions, x equals 1/8 or 3, okay? And now to find y from these, I can go back to this equation and I can say that 25 times x minus 3 is going to give me 3y. So y on its own is going to be 25x over 3 minus 1. So let's do the case of x is equal to 1 over 8. I have 25 times 1 over 8 over 3. That's 25 over 24 minus 1, and 1 is 24 over 24. So that means that y is equal to 1 over 24. Or if x is equal to 3, then 25x over 3 is just 25, and minus 1 gives me 24. Now it's very important when you're writing the solutions to questions like these, where there's one x solution with one y solution, that you write them as a pair. You explain which one goes with which. So I have 1 over 8 and 1 over 24, or 3 and 24. You won't get the final marks if you don't do this, because if I have x equals to 1 over 8, that does not work with y is equal to 24. And you need to make that clear. And it's enough to just write them next to each other, or to label, or to make maybe even an arrow between the solutions that work together. But make sure you indicate which pairs work. We had 3/24 or 1 over 8, 1 over 24. And that looks good. Perfect. All right, now we have a harder question where we have a chain of logs. We have log base 2 of 3 times log base 3 of 4 squared, etc., up to log base 7 of 8 to the power of 6. Okay, so we're going to start by taking out all of those constants. So I have 4 to the power of 2, 5 to the power of 3, 6 to the power of 4. I can take out all those constants. I'm going to have 2 times 3 times 4 times 5 times 6, taking all of those constants out. And that's just going to multiply log base 2 of 3 times log base 3 of 4 times ... times log base 7 of 8. Okay? And this whole thing here is going to evaluate to 6 times 4 is 24 times 5, or times 30. So I'm going to do 24 times 30. 24 times 3 is 72, times 10 is 720. And now I'm going to rewrite each of these logs using the log change of base. So I'm going to write log base 2 of 3 as log 3 over log 2. I'm going to write log base 3 of 4 as log 4 over log 3. The next one is going to be log 5 over log 4, log 6 over log 5. Let's make some room. Sorry, it's going to take a second, log 7 over log 6 times log 8 over log 7. That's the last one. And now notice that I can cancel a lot of these logs with each other. And all I'm left with is 720 log 8 over log 2, which is the same thing as 720 log base 2 of 8. And log base 2 of 8 is 3, so this is 720 times 3, which is going to give me 3 times 700 is 2,100, and 3 times 20 is 60, so 2160 is the answer. 2160. In what scenarios are change in base most useful? How do we know when we use it again? So primarily you're going to use the change of base when you have an equation that has two logs in different bases. So let me scroll back to the earlier example. This was the first one, I think, where we used the log change of base. In the first equation, I have a log base 4 of x, and I have a log base 2 of 3y. And it's very, very difficult to do anything with logs unless they're in the same base, because all of the other rules we have are for logs in the same base. So it's a preparation step that allows us to use the rules. And you should be thinking about doing it whenever you have logs that are in different bases in an equation. It was the same thing here. I had all these different logs in base 2 and 3 and 4. And there's no good way to simplify those except maybe to change the base. So the key signal for log change of base is when you have logs with different bases in an equation or expression. I hope that answers your question. Next, we're going to talk about exponential functions. So a function of the form f of x is equal to a to the power of x, where x is some base. So the key thing to focus on is when I have a to the power of x, if I go from somewhere on a curve and I go over by 1, so I do x to x plus 1, then a to the x plus 1 is equal to a times a to the x. Okay, that's a to the 1, which means every time I go over by 1 to the right on the curve, I'm going to go up times a. I'm going to multiply by a. And that's the defining behavior of an exponential function, which is that its vertical component gets multiplied for a constant shift in the horizontal position. Okay? So I've graphed on this diagram a couple of different exponential functions. I've shown 2 to the x, 3 to the x, and 5 to the x. You notice that they get steeper and steeper as I raise the base, but they all pass through 0, 1. And that's just because anything to the power of 0, a to the power of 0, is going to give me 1 for all numbers a. Okay? You also notice that these all have a horizontal asymptote at y is equal to 0. Something to the a to the power of x, where a is a positive number, or a real number, sorry, is never going to be negative. Okay, I can't get a negative number by doing 2 to the power of something. So let's move to the next slide. I'm going to give you a minute to solve this question about the range of this function. I have f of x is equal to 1 minus 3 to the power of 2x minus 1. And I'm trying to find the range of f. So remember that 3 to the power of some number is always going to be positive, right? So 3 minus something that's always positive can never, ever be bigger than 1. Now, at the same time, it's never going to be 0. 3 to the power of something is never going to be 0. You know, I can do 3 to the power of negative a million or negative 1,000. That's going to be 1 over 3 to 1,000, which is going to be very close to 0, but it's not going to be 0, which means that f of x can never actually be equals to 1. So the upper bound on f of x is going to be 1, but it's not going to be inclusive. All right? And there's also going to be no limit on how negative f of x can be, because I can just keep making x bigger, and that negative 3 to the power 2x minus 1 is going to keep getting more negative. So negative infinity is my lower bound. So I'm going to go from negative infinity to 1 is the answer. Okay? Now the y-intercept. Well, the y-intercept of a function is just where it crosses the y-axis, and the y-axis is defined by x is equal to 0. So I plug in 0, and I'm going to get f of 0 is 1 minus 3 to the power of 2 times 0 minus 1, which is equal to 1 minus 3 to the minus 1, which is 3 over 3 for 1 minus 1 over 3, is equal to 2 over 3. That's option 2. And now the x-intercept, slightly harder, but the x-intercept is when this whole thing is going to be equal to 0. So f of x equals 0. 1 minus 3 to the 2x minus 1 is equal to 0. So 3 to the 2x minus 1 is equal to 0. Sorry, to 1. And 1 is the same thing as 3 to the power 0, which means that 2x minus 1 must be 0, which means that x is equal to 1/2. Boom. So here I have a graph of an exponential function, and I want you to find its equation using things you can see in the graph. So I have an exponential function, and it has a horizontal asymptote at y is equal to negative 18. And I'm trying to write it in the form f of x is equal to some constant c plus a to the times b to the power of x. And I'm trying to find c, a, and b. Okay? So first of all, because I know that there is a horizontal asymptote at y is equal to negative 18, I know that as x goes to minus infinity, as this term goes to 0, and I should put the x back. As this term goes to 0, I'm going to be left with more or less just c. So that's got to give me my horizontal asymptote, which means that c is equal to minus 18. That's the first thing. Okay? And we also know that the point 0, comma, negative 16 lies on the curve. So if I plug in 0, f of 0 is equal to now negative 18 for c plus a times b to the 0, and b to the 0 is going to be 1, which means I have negative 18 plus a is equal to negative 16. So a is 2, right? That's the next thing I know. So now the last piece of information I have is that the curve goes through 2, comma 0, which means that f of 2, which is now negative 18 plus 2 for a times b, and now x is 2, is equal to 0, which means that 2b squared is equal to 18, which means that b is plus or minus 3. But because I can tell that this curve is increasing and the base has to be positive, I know that it's going to be plus 3. So we are looking for 2 times 3 to the x minus 18. And that is option number 3 here. Nice. Now, log functions. So if I have a function in the form log base a of x, then first of all, I remember we said earlier, I can only find the log of a positive number. So x has to be greater than 0. I can't say log base a of 0 because there's no power I can put on a that's going to give me 0, right? I can do a to the power of negative 1,000. It's going to give me a small number, but it's not going to give me 0. It's never going to give me 0, and it's never going to give me a negative number. That means that the domain of a log function is x greater than 0, as long as it's just an x in the argument. And here in this diagram, I've plotted a couple of different log curves, and you can see that the higher the base, the slower the curve increases. So this is log base 5, log base 3, and log base 2. What do they have in common? They have in common they go through 1, comma 0. Because log base anything of 1 is just 0, because any base to the power of 0 gives 1. Now, maybe you're already seeing that there's something similar between this and the graphs of exponential functions in that there's different steepness depending on the value of a, but they all pass through 1 on either the y-axis or, in this case, the x-axis. We're going to talk more about that connection in just a sec. But before that, I want you to find the domain and range of this logarithmic function. Okay, let's start. So I have f of x is equal to 2 minus log base 3 of 9 minus x squared. So the only reason the domain is going to be restricted here is because, like I said, what goes inside the log has to be positive. It can't be 0 or negative, which means that 9 minus x squared is greater than 0. And that means that x squared is less than 9, which means that negative 3 is less than x is less than 9. When I take the square root of both sides and I put a plus minus, I just have to be careful because it's an inequality. Remember, x squared looks like this, and the line 9 is here, and we're looking for this part of the line, the part where it is negative. So it's between the two roots of x squared equals 9, okay? So that is the answer to part A. It should be negative 3 to 3 exclusive. And now for part B, the range of f, well, we realize that, again, log base 3 of 9 is only defined for when 9 minus x squared is positive. So let's think about when log base 3 of 9 minus x squared is biggest. So log base 3 of 9 minus x squared has a max when x squared is 0, when the inside is maximum, and the 9 minus x squared is never bigger than 9. So max at log base 3 of 9 is equal to 2, which means that the minimum value of f is when I do 2 minus the maximum value of the log. So the minimum value is 2 minus 2 is 0, and that is inclusive because the log base 3 of 9 actually does reach the value 2. Okay, so 2 minus 2 is the minimum value of x. And what's the maximum? Well, log base 3 of 9 minus x squared can be arbitrarily small. If I do log base, 9, log base 3 of 9 minus, and I do 2.99 squared, you can type that on your calculator. I'm going to do it just to give you an accurate number. So I do log base 3 of 9 minus 2.99 squared is going to give me negative 2.56. But in general, I can do even more nines. I can do, 999. And I can get negative 20. I can get as negative as I want the value to be, which means that since I'm doing 2 minus a log, and the log can be arbitrarily negative, I'm doing actually 2 plus a number that can be as big as I want. So this has an upper bound of infinity. Okay, that's a little bit of a tricky question, but we got to the end of it. So 0 inclusive, infinity exclusive. Now, this was the symmetry I was talking about a second ago, the connection between the functions of log and the functions of exponentials. So if you actually draw the graph of a to the power of x for some value of a, and you draw the graph of log base a of x, you'll notice that they're mirror images of each other. And if you remember the class we did on function theory the other day, we know that inverse functions are the mirror images of each other in the line y is equal to x. Now, why would a of x and log base a of x be inverses? Well, if you think about it, if I take log base a of a to the power of x, if I plug one function into the other, that should just give me x. And if I do a to the power of log base a of x, so putting the other function into the second one, I just get back x. And that's the definition of inverse functions, is that I put one into the other and I get x, which means that these two functions are inverses, and that explains why their graphs are symmetric like this. Okay, so I have a function, 2e to the x minus 4. I want you to find f negative 1. I'll give you 30 seconds. Let's solve this question. So I'm going to start by writing this as y is equal to 2e to the x minus 4. And to find an inverse function, I swap the x and y. So I'm going to write x is equal to 2e to the y minus 4. And now I'm trying to isolate y. So how do I do that? I add 4 to both sides. 2e to the y is equal to x plus 4. Dividing by 2, that gives e to the y is x plus 4 over 2. And now I take the log base e of both sides, so the natural log of both sides, to isolate y is equal to ln x plus 4 over 2. Let's answer number 1. Next question. Okay, I didn't actually show you the graph of the natural log function, so I'll do that now. But we know that e is some number that's 2.7, so it's between 2 and 3, and it's slightly closer to 3. And you can see that on the graph of the natural log if you also plot the log base 2 of x and log base 3 of x. You'll notice that the curve for ln is very close to 3, and it's between the two curves for log base 2 of x and log base 3 of x. Okay? Now, some exam-style questions on log functions. We have, I think, 5 questions left to do today, and they're all pretty tricky. So it should take another, I'd say, 45 minutes to an hour. So I'm going to give you a minute to get a head start on this question in case you want to get ahead of me, and then I'm going to start solving it. Okay, let's start. I'm going to make some room on the right-hand side. And I know that the point 2, 2 lies on the graph of f, which means that f of 2 should be equal to 2. Let's plug that into the expression. Log base 2 of the square root of 4 times 2 plus k should be equal to 2. In other words, if I raise both sides to the power of 2, I get the square root of 4 times 2 plus k should be equal to 4. So root of 8 plus k is equal to 4, which means 8 plus k is equal to 16. So k is equal to 8. And that's how you would show part A. Let's just check that off quickly in the mark scheme. Yeah, we did that. And we did that. Now, we're trying to write down the largest possible domain of f, okay? So remember, when I have a log function, the inside of the log can't be negative, but in this case, that's not really a problem because a square root can never give a negative number. But it does mean that the square root has to be defined and positive. So the square root has to be 4x plus k, in this case plus 8, is greater than 0. And it's not greater than or equal to 0 because if I put 0 into the log, it's going to break. So it's not just that the square root can't be negative, but also can't be 0. All right? So if that's greater than 0, it means that 4x plus 8 is greater than 0, which means that 4x is greater than negative 8. X is bigger than negative 2. And that's the answer to BII, or BI, I mean. And then for BII, the largest possible range of f, well, let's take a look at the square root. If I take the domain that we just found, which is x greater than minus 2, then the expression which I have inside the square root, 4x plus 8, is always positive, like we said. And as x gets very, very close to minus 2, the square root goes to 0, okay? And as the square root goes to 0, the log base 2 is we're going to get closer and closer to the log base 2 of 0, which is going to be negative infinity. So the minimum value of this is going to be negative infinity. And then the maximum value is going to be, well, as x goes to infinity, I'm going to have 4x plus 8 is going to approach infinity. The square root of that is also going to approach infinity. So that is also going to go to infinity. Okay, so my range should be negative infinity to infinity. So on the axes below, we want to sketch this function. All right, so what do I know? Okay, there we go. I know that at x is equal to minus 2, the function is undefined, right? I can't put in 0 into the log. And I also know that as I get close to minus 2, like I said in the previous part, we're going to go to minus infinity, which means that I have a vertical asymptote at x is equal to minus 2. I also know that we pass through the point 2, comma 2. Now, the only thing I have left to figure out is what is my y-intercept going to be. So when x is equal to 0, I have log base 2 of the root of 8, log base 2 of root of 8, which is log base 2 of 8 to the 1/2, which I can write as log base 2 of, and remember 8 is 2 cubed, so this is 2 to the 3/2, so it's going to be 1.5. So the y-intercept is going to be here at 1.5. And if I graph that, I'm going to get something, it's a little bit hard on my iPad to sketch this, but something that looks like that. There we go, and it keeps going up. And the question is, where is the x-intercept going to be? Well, the x-intercept is when log base 2 of root 4, f of x is equal to 0, so f of x is equal to 0. That means that log base 2 of root 4x plus 8 is equal to 0. I'm going to take the square root outside and do 1/2 log base 2 of 4x plus 8 is equal to 0. Okay? And I'm going to write 0. I'm going to just, the half makes no difference. The half is not 0, so that has to be the log that's 0. So log base 2 of 4x minus 8 is equal to log base 2 of 1, right? Because log base 2 of 1 is 0. So 4x plus 8 is equal to 1, which means that 4x is equal to negative 7. That gives x is equal to negative 7 over 4. All right, is that clear? So I was slightly off. It should be about here at negative 7 over 4. And this is 1.5. Okay, I would probably draw it better if I was using an actual pencil, but I can't get a perfect drawing with my fingers. The functions f and g are defined by f of x is equal to 2 to the power x plus 1 plus 2, and g of x is equal to 1 minus 2 to the minus x. And we're told that f of a minus g of a is 11 over 2. All right, so I'm going to start by setting that up using the expressions that I have. So f of a minus g of a is equal to 2 to the a plus 1 plus 2 minus 1 minus 2 to the negative a. Okay, and that's supposed to be equal to 11 over 2. So what does this become if I write this out? I have 2 to the a plus 1, and I have plus 2 minus 1 is plus 1, and then plus 2 to the minus a is equal to 11 over 2. Okay, so this is a bit tricky, but you have to recognize here that we have something that's actually pseudo-quadratic. We have a quadratic that's hidden from us here. And to show you where the quadratic is, I'm going to multiply everything through by 2 to the power of a. But first, I'm going to bring the 1 to the other side and simplify to 2 to the a plus 1. Sorry, 2 to the a plus 1 plus 2 to the minus a minus 9 over 2 is equal to 0. And now multiplying through by 2 to the a, I get 2 to the 2a plus 1 plus, and then 2 to the negative a times 2 to the a is 2 to the 0 is 1, minus 9 over 2 times 2 to the a is equal to 0. And if I recognize that 2 to the a plus 1 is 2 to the 2a times 2 to the 1, this is going to be 2 times 2 to the a minus 9 over 2, and this is supposed to be a 2 here, 2 to the 2a minus 9 over 2 times 2 to the a plus 1 is equal to 0. Okay? And now, if I let y be equal to 2 to the a, then I'm going to get 2y squared minus 9 over 2y plus 1 is equal to 0. How do I solve that? Well, I am going to use my quadratic equation. Make some room here. We're going to say that y is equal to negative b, so in this case 9 over 2 plus or minus the square root. B squared is 81 over 4, 9 over 2 squared, so 81 over 4 minus 4 times 2 times 1. All that over 2 times 2 is 4. Okay, so that's going to be 9 over 8 plus or minus. Now I have the square root of 81 over 4 minus 8. And 8 is the same thing as 32 over 4. So it's 81 minus 32 all over 4. And 81 minus 32 is 49. So this is the root of 49 over 4 all over 4. Okay? 49 is the square of 7, and 4 is the square of 2. So this is 9 over 8 plus or minus 7 over 2 over 4. In other words, 9 plus or minus 7 over 8. What two values does that give me? That gives me either 16, 9 plus 7 over 8, so that's 2, or 9 minus 7 over 8 is 2 over 8 is 1 over 4. So those are the two possible values of y. But I was trying to find a, and y is equal to 2 to the a. So that's 2 or 1 over 4. So if 2 to the power of a is 2, that means that a is equal to 1. And if 2 to the power of a is 1 over 4, well, 1 over 4 is 2 to the minus 1, sorry, to the minus 2. That makes a equals minus 2. So these are my answers. This is going to be another pseudo-quadratic question. I have f of x is equal to 2e to the 2x minus kx, ke to the x plus 18, and I'm told that the function is positive definite in part A. What do I know? I know that f of x is positive definite, which means that f of x has no roots. It doesn't intercept the x-axis anywhere. Okay, so what does that mean? It means that if I take this f of x and I say y is equal to e to the x, then f of x, maybe I'm going to use u actually. It'll be better with u. Let's say u is equal to e to the x, then f of x is 2u squared minus k u plus 18. And we're told that k is greater than 0. Okay, so if the function is positive definite, it's because there are no roots. If there are no roots, it means the discriminant is negative. So delta is equal to b squared minus 4ac is less than 0. In this specific case, that means that negative k squared minus 4 times 2 times 18 is less than 0. Or in other words, k squared is less than, and I'm going to do 4 times 36 on the right-hand side. I'm leaving it that way because easier to take the square roots. So that means that k is going to be between, if I take the square root of 4 times the square root of 36, that's negative 2 times 6. So negative 12 on the left-hand side and positive 12 on the right-hand side. But I know that k is positive. That's given in the question, which means that actually this must be 0. So k is between 0 and 12 is the answer to A. Part B. Now we're given that the function has a unique solution, so it's a slightly different case. We know that now that delta is equal to 0. And if I just remind us that f of x was equal to 2u squared minus ku plus 18, where u is equal to e to the x, then delta is equal to 0 means that k squared minus 4 times 18 is equal to 0. And sorry, 4 times 36 is this 4 times 2 times 18. 4 times 36 is equal to 0, which means that k squared is equal to 4 times 36. So that's 2 squared times 6 squared, which makes k equal to 2 times 6 is 12. All right, that's the answer for part B, 12. And now finally, part C. For the value of k found in B, so k is equal to 12, solve the equation f of x is equal to 6. Okay, so I have 2e to the 2x minus 12e to the x plus 18 is equal to 6. All right, I'm going to cancel 6 there and replace 18 with 12. And then I have 2e to the 2x, 12e to the x, and 12, so I'm going to divide by 2. So I have e to the 2x minus 6e to the x plus 6 is equal to 0, right? And again, I have to recognize that I have a quadratic here. And if I do that, I'm going to let, again, u is equal to e to the x, and I have u squared minus 6u plus 6 is equal to 0. I use the quadratic equation. U is equal to 6 plus or minus the square root of 6 squared minus 4 times 1 times 6 over 2 is 6 plus or minus the square root of, and this is going to be 36 minus 24 is 12 over 2. So this is 3 plus or minus, and 12 is 4 times 3, so root 12 is going to be 2 root 3, and over 2 is plus or minus root 3. And those are the values for u, by the way, not the values for x. So to convert those back into x, we remember that u is equal to e to the x. So x is equal to ln of u. So x is either ln of 3 plus root 3 or ln of 3 minus root 3. And those are our answers. Why do I use, okay, so 2 questions. Can you please explain the positive definite terminology again? You can see it in IB. It was used in questions on the previous syllabus. I don't know if they've used it since 2021 on the exams. I'd have to actually check to give you a 100% answer about that. But to be safe, you should 100% know what it means. And positive definite just means that it's always positive. It's always above the y-axis. So positive just means greater than 0, and definite essentially means everywhere. No matter where I go for x, I'm always going to be positive. So positive definite, stuck or defined on the positive side, okay? Now the second question is, why do I use u substitution? Isn't that used in calculus? So yes, it is used in calculus with a very different purpose. So in calculus, I use u substitutions to solve integrals. There is, I guess, one similarity between what I'm doing there and what I'm doing here, But the point of doing a u substitution is only to make my work easier, to recognize that I'm a human, I'm not a supercomputer, and actually keeping track of everything that's happening can be very, very hard. So when I look at this function, for example, and I have 2e to the 2x minus ke to the x plus 18, I can tell that there's a quadratic there because I have e to the 2x and e to the x, but it's much easier for me to understand that quadratic if I just replace e to the x with u, because then I'm going to get something with u squared and u, and it's going to be much more familiar and much more comfortable. I'm much less likely to get confused about what the coefficients of the quadratic are, and I'm less likely to make a mistake. You don't have to do a substitution, but I strongly recommend it. And you can use it in other contexts too, right? It's just about renaming something that's complicated with something simple because that complicated thing shows up in multiple places. And so we want to kind of ignore it. Hope that helps. Let's go to the next question. All right. Uh, if we were still wondering about u subs, we're going to do one again here. So it's another chance to review it. But basically, I have another pseudo-quadratic question. These are overall pseudo-quadratic questions are very common on the IB, especially at higher level. But here I have an equation that involves 2 to the x and 2 to the minus x, and also this 11 over 2 and this plus 1. So if I bring everything to one side, I'm going to have 2 times 2 to the x minus 9 over 2. Yeah. Plus 2 to the minus x is supposed to be negative, or negative definite, by the way. It means the same thing here. And what I'm going to do for the sake of clarifying how this is a quadratic is multiply through by 2 to the power of x. So this gives me 2 times 2 to the power of 2x, because 2 to the x times 2 to the x is 2 to the 2x, minus 9 over 2 times 2 to the x. And then 2 to the negative x times 2 to the x is 2 to the 0 is 1. And that's less than 0. And now here's where the u substitution is. I notice that I have 2 to the 2x, which is 2 to the x squared, and I have 2 to the x. Now, for the moment, I don't want to think about 2 to the x, so I'm going to say u is equal to 2 to the x. You don't have to do this. It's just a step that's going to help in the working and keeping my work clear and make it less likely that I make a mistake. Then what I have is 2u squared minus 9 over 2u plus 1 is less than 0. Okay? And if I use my quadratic equation to find when it's equal to 0, so equals 0 when u is equal to 9 over 2, make that a bit clearer, 2, plus or minus the square root of, and b squared here is 81 over 4. This is actually an identical quadratic to one we had a second ago. 81 over 4 minus 4 times 2 times 1 over 2 times 2 is 4. So this is 9 over 2 plus or minus, and then I have 81 over 4 minus 8, and 8 is 32 over 4, so 81 minus 32 over 4, and that's just going to be 49 over 4, so square root of 49, not 99, 49, 49 over 4, all over 4. And the square root of 49 over 4 is 7 over 2, so 9 over 2 plus or minus 7 over 2 over 4, which is either 9 plus or minus 7 over 8. That is either 9 minus 7 is 2 over 8, 1 over 4, or 9 plus 7, 16 over 8 is 2. So that's what 2 to the x is equal to, 1 over 4 or 2, which means that x itself is either minus 2 or 1, right? Because 1 over 4 is 2 to the minus 1. And we're looking for where this quadratic is less than 0. And it's a quadratic in u squared, which means it's a quadratic that is concave up, right? Because there's a positive u squared. So looks something like, let me zoom out, something that looks like this. And we found there was a root at 1 over 4 and 2. And we're looking for this region, the negative region, which means our answer is it's a exclusive inequality. So we're looking for x is bigger than -2 and less than 1. That is my answer. We have another question. Why do you multiply 9 over 2 with 2 to the power of x? So let me maybe go back and just show the working again. So I had this equation where I had 2 times 2 to the x minus 9 over 2 plus 2 to the minus x. And this step takes a little bit of experience, but the point is that you're going to quite often, I'd say on average, one time on the IB in some question, you're going to end up with some kind of a pseudo-quadratic where you have a term to the power of x or to the power of something, and then to the power of negative something. And in general, I don't know how to solve that equation because we don't, unless you have a calculator. But what I notice is that if I multiply everything here by 2 to the power of x, then I would get this. So I multiply each term individually by 2 to the power of x, and it's going to turn into a quadratic. So that's specifically what I'm doing, is multiplying this by 2 to the power of x so that I have a form that I know how to solve. And when I multiply by 2 to the power of x, that also applies to 9 over 2. So each term gets multiplied by 2 to the power of x. How do you know if it's exclusive or inclusive inequality? Well, the question tells me that it's exclusive, right? So it tells me less than 11 over 2 and not less than or equal to. If it said less than or equal to, well, then I would have to include the values where this was equal to 11 over 2. But the question says no, the question says less than. So you have to pay very close attention to the question. Okay, let's get started because this is a tricky question. So let's decipher what it's saying first. I have a sample of 2 radioactive isotopes. Each of them has an initial mass of 1 kilogram, and they're prepared in the Perplex laboratory. See, we made these samples. Over time, the mass of the samples will decrease due to radioactive decay. All right, so the mass is going to decrease over time. And we have these equations that tell us the mass of sample A and the mass of sample B in kilograms after t years. So the mass of sample A is e to the negative small at, and the mass of sample B is e to the power of negative small b times t. And we're told that B is greater than A is greater than 0. Pay attention to this fact. We're going to need it in a second, okay? We're going to need it in, I think, part C or D. So the first step is to show that m of t, which is the combined mass, satisfies this equation. So let's first write out what the combined mass is. So m of t is equal to e to the negative at plus e to the negative bt. All right? And the question wants us to show that if I take m of t and I square it and I subtract m of 2t, I get 2at bt. Okay, so let's start by squaring m of t. If I square m of t, actually I'm gonna write this over here. If I do m of t squared, I'm gonna get e to the negative at squared plus 2e to the negative at times e to the negative bt plus e to the negative bt squared. That's just the expansion of a plus b squared. I'd square the first term 2 times the cross term plus the second term squared. Okay? And if I then evaluate m of 2t, which is the second thing the question is asking, I get e to the power of negative 2at plus e to the power of negative 2bt. All right? And m of t squared simplifies to, if I expand it out, e to the negative at squared is, according to the rules of exponents, negative 2at, and then plus, and here I'm going to have 2e to the power of e to the negative at, e to the negative bt, and then plus e to the negative 2bt. And notice then that the only difference between these two is what I have in the middle, this term here. So if I do the subtraction, m of t squared minus m of 2t, I will get 2e to the negative at, e to the negative bt. But that is just, according to the definitions of a and b, 2 2a of t, b of t, which is what we wanted to show. So that's perfect. We have that identity, and that's done. So let's check that off. We found that, and then we subtracted. Cool. Part B. So after 100 years, the combined mass remaining is 800 grams, and after 200 years, the combined mass is 400 grams. Okay, so I'm going to write t is equal to 100 years, and that means that after 2t is 200 years. All right, and that actually lines up, you see, with the 100 and 200 that I have here in the question. And then the question is telling me that the combined mass at 100, which is, I said was t, m of t is equal to 800 grams, which is 0.8 kilograms, and that m of 2t is equal to 400 grams, so 0.4. And I have an identity from part A that says if I take the square of this and I subtract the second one, I should get twice the product of the individual masses. So if I do m of t squared, I get 0.64. And then I subtract, I'm going to subtract m of t, and that's going to tell me that m of t squared minus m of 2t is equal to 0.64 minus 0.4 is 0.24. That's equal to 2a of t, b of t. All right. What does that mean? It means that if I write 0.24 as 24, actually, I'm not going to do, yeah, I'll do 24 over 100. That's fine. 24 over 100 is equal to 2a of 100, b of 100. And I divide by 2 on both sides, and I get 12 over 100 is equal to a 100, b 100. And now 12 over 100, if I divide by 4 on the top and the bottom, is 3 over 25. Which means that if I now divide on both sides by a 100 to isolate b 100, I get the desired result, b of 100 is equal to 3 over 25 a 100. All right, I know that's a bit tricky. I have a question here. I'm going to try and answer this. Can you please explain this question again? And that was 3 minutes ago. Yeah. So, okay, I'm gonna just explain one more time from the top to see if I can help dispel this. So I have two blocks. I have a block which is made of some piece of metal and a block that's made of another piece of metal. And you don't have to take physics to understand this, but it is a fact in physics that certain types of elements decay over time. That's how nuclear energy works. You have a mass that's going to lose some of its mass over time, and the speed at which the mass is lost depends on what it is. So, for example, uranium decays very, very quickly, which is why it's such a dangerous element to carry around the house. And we don't know exactly what the elements are here, and we don't really care about the physics. We're just given an equation for the mass over time, right? So the mass of the first one is e to the power of negative at, and that means that when t is 0, if I plug in t as 0, I get e to the power of 0. I get 1 kilogram as the starting mass. And b also is going to be 1 kilogram of starting mass. And then as time goes on, the masses are going to decrease. So they're going to start at 1. They're going to start at 1, and they're going to decrease over time, like a shape like this. They're going to exponentially decay. And part A is simply asking us, this is definitely a HL question, by the way. It's asking us to demonstrate an identity about the combined mass. So m of t, which is equal to a of t plus b of t, is if I were to weigh the two blocks together, what would the mass be, right? And I'm calling that m of t. And we notice by doing some algebra that m of t satisfies this property, that if I take m of t and I square it, and I subtract m of 2t, I just get 2a times b. And that's going to be useful for subsequent parts of the question. Okay, I hope that helps. I know it's still not an easy question, but but bear with me and you can revisit it. There's a solution on the website. Um, you can also chat with the AI if you're still confused. Answer. So that was the answer to part B. So I'm just going to clear my screen and I'm going to check off part B. We showed all of this. Perfect. And now part C. We're trying to find A of 100. Okay, so this is a little bit of a tricky part, but basically we're going to use what we know about the total mass after 100 years and the relationship between the mass of B after 100 years and the mass of A after 100 years. Okay, so I'm going to denote for now, I'm going to say A is just going to stand in for A of 100. So I don't have to write 100 every time. And similarly for B, that's going to be B of 100. All right. And then I know that the total mass after 100 years is 0.8. And that's the combined mass of A plus B is equal to 0.8. And I know from part B that I have this relationship between B and A, which was that B is equal to 3 over 25A. So now I can rewrite this as 0.8 is equal to A plus 3 over 25A. Okay, phew, that's a bit of a mess, but we can rearrange this. I have A in a fraction. I don't like it in a fraction, so I'm going to multiply both sides by A, and I get 0.8 A is equal to A squared plus 3 over 25. And just to help us with the algebra, I'm going to rewrite 0.8 as 4 over 5. Now, I don't like this 3 over 25, but it's actually probably going to be easier to leave it in for now to help us solve the quadratic, right? So if I actually, it probably will be easier if I'm going to multiply both sides by 25 now, and I'm going to get 4 over 5 times 25 is going to be 20a is going to be equal to 25a squared plus 3. Rearranging everything, I get 25a squared minus 20a plus 3 is equal to 0. All right. Now, let's use the quadratic equation. A is equal to, I'm going to take my time with this one because it's going to be a mess otherwise. Let's do a nice perfect square root so that this is very clear. Now, negative b, so I'm going to do 20 plus or minus b squared is 400 minus 4 times 25 times 3. And that's all going to be divided by 2 times 25, which is going to be 50. All right, what is that equal to? 20 plus or minus. And now 4 times 25 is 100, times 3 is 300. So under the square root, I have 400 minus 300 is the root of 100. And that's all being divided by 50. Okay, so this is going to be 20 plus or minus 10 over 50. Or in other words, I either have 10 over 50 is 0.2, or 20 plus 10 is 30 over 50 is 0.6. Now, the question is, which one of these is the answer? And this is probably the hardest part of the question, is to realize that the total mass after 100 years of A plus B is supposed to be 0.8. So if this is the mass of A, then that would mean that B has a mass of 0.6, and that would mean that B has a mass of 0.2. Okay? And now, like I said earlier, we have to pay attention to the fact that the question says that B is greater than A. So this B is greater than A tells me that B is going to be decaying faster than A. If I were to draw what these decays look like, A is going to be decaying like that, and B is going to be decaying like that. It's going to be decaying faster, which means at any time after 0, specifically at 100 years, B is going to be lighter than A, which means I cannot have 0.2 for A and 0.6 for B. So the answer is A is equal to 0.6 kilograms. I've got a question here, so I'm going to answer it. Where did you get 20A from? Okay, let's go back and see. All right, so I had 4 over 5. I'll write it out separately over here. 4 over 5A, and I multiplied both sides by 25. Okay, and 25 is 5 times 5. So one of those 5s cancels with the denominator of 5, and I get 4A times 5, and that is 20A. Okay. So that definitely is the hardest part of the question, but we found A is 0.6. Let's check that off. 0.6 kilograms. And now part D, we want to find the exact value of A. A is the little coefficient up there in e to the power of negative AT. Okay, so I know that A of 100, we just found was 0.6, is the same thing as e to the power of negative A times 100. All right, so what am I going to do? I'm going to write 0.6 is 3 over 5 is equal to e to the power of negative 100A. And now I'm going to take the natural log of both sides, right? So ln of 3 over 5 is equal to negative 100A. Okay? And ln of 3 over 5 is ln of 3 minus ln of 5. That's minus 100A. And that means that A is equal to ln of 5 minus ln of 3 over 100. And I switched the direction. I did ln 5 minus ln 3 because I was dividing by a negative number, okay? So, very hard question, guys. Thank you for powering through. That is everything I wanted to cover today. So now is the time to ask any general questions you might have or give us any feedback you have about today's session, anything we can make better. Let us know. Otherwise, if you have nothing to say, feel free to head out whenever.